Thank you very much, Elke. I'm very happy to be here. I'm honored to be invited here. There's such a big crowd. In Belgium, we usually don't get these big crowds to talk to related to post-harvest technology, although we are also quite a big industry, but it's quite condensed. So I'm very happy that you're all here, and I hope I can share with you some of the latest findings that we are having in the research that we are doing. Mainly on palm fruit, following the introduction, maintaining the quality also after harvest of those fruits is a main challenge. Specifically, if you look at these numbers right here, you see how losses across different products are today still an issue. These are data from the Food and Agriculture Organization of the United Nations that have established these data across the world, and you see fruits and vegetables are still up there, second ranked, with losses more than 20% in the post-harvest chains up to the consumer. So this is without considering the waste that is happening at the consumer side. So this is everything that is happening at the industrial side. We're still quite concerned about these numbers. Certainly, if you look at also the right-hand side figure here, that kind of gives an idea how these losses are evolving over the years, considering a benchmark year 2015 and then analyzing it again in 2021. You see the numbers there are largely, mainly above 100, saying that the issue is we're not decreasing the issue, and in fact, it is kind of a growing issue, which is, I think, should be a common concern for all of us, trying to get these numbers down instead of keeping them increasing. So there are quite some challenges in the post-harvest supply chain. You do a lot of effort to produce these nice fruits in the orchards a year. It takes you half a year to get at good harvest maturity and good quality at harvest. Still, things can go wrong with things that might have happened already during the growing and that can continue to cause problems in the post-harvest supply chain, like, for instance, insects infestations. I will be showing some examples of how we can deal with that, trying to avoid these fruits getting into the supply chain. And then secondly, you go into post-harvest storage, which is also for palm fruit definitely quite a long period. It can be up to 9 months or storage. And if you don't manage your storage rooms well, then all kinds of problems can occur there as well. And I will be talking about these issues as well. So the title of the presentation is quite broad, actually, and I hope I meet up to some of the expectations that is raised by the title, but we'll be looking at some examples in more detail. So the title is Advances and Challenges in the Use of AI for Post-Harvest Application. I will be mainly talking about sorting, quality sorting, and how AI can help us improving quality sorting, and I will also be introducing a novel method for quality sorting based on X-rays rather than on conventional vision technology. So as a whole, I hope to introduce some of the novelties that are happening certainly in research, but maybe I'll be able to show you as well that we're making quite some advance and getting ready actually to introduce those methods also in practice. This is not only my work, I'm just a supervisor of the team, let's say, but the main work is done by our PhD students that are listed here. And as well, my co-supervisor or the head of our team, Bart Nicolai. So it's about sorting for quality, and I'm sure, as you are all industry-related people here, you know that these technologies are in place and they work quite well for evaluating external quality. They image each individual fruit from multiple perspectives, so there's nothing to hide in one of those pictures, and you take sometimes more than 30 pictures for a single fruit. And so you will be able to detect problems that are occurring on the surface of the product, like this, for instance, this spot here that might be originated from maybe some damage that occurred during the handling, and you want to avoid that fruit to go into the rest of the chain, and then maybe also damaging other fruits, etc. later on, or dissatisfying the consumer in the end. So these systems exist and they're quite reliable, I believe, and most of you are, I hope, quite happy with the technologies that are being supplied today. I'm just showing 2 examples here of companies, but there are many other players, of course, supplying these type of systems. Where things are still quite a challenge is when we talk about internal quality, and definitely when we narrow down internal quality to defects that are not visible from the outside, like these ones here. And you see an example of Braeburn apples that have been stored on the left-hand side in the proper way with the optimal conditions, and on the right-hand side in conditions where we have forced them to create a problem in this case, but you know, in practice, it's also not always very clear which are the optimal conditions, and even when you think you're putting them in the right conditions, they might still end up the way they look on the right-hand side. And this is also because we don't completely understand the physiology behind this disorder development as such. But that's a whole story on its own, and maybe the next speaker will talk a little bit about that as well. But in my talk, I will be more focusing on how can we detect these problems without having to cut open the images like you would have to do here, which would be batch-wise inspections, and then you would cut open a few of these sample of fruit, and then you will have to decide to discard the whole batch while there might still be fruit in there that are perfectly sound, and we try to avoid having to waste also good fruits when detecting these defects. So we need non-destructive methods to do that, and there are some methods on the market already based on NIR, but also from our own experience, we see that the method might not be that robust yet. It requires a lot of calibration on site, and I trust you might have the same experience. So we're continuously looking for new methods to maybe circumvent that problem of severe calibrations needed to do proper sorting. And X-ray imaging might be one of those methods that might help us to do so. The properties of X-rays are beneficial for this task. It's a kind of electromagnetic wave, as you see here in the scale of typical electromagnetic waves that we use in common sorting are the visual ones and the infrared ones. They're quite long wavelengths with respect to X-ray, which has very short wavelengths. The advantage of the short wavelengths is that it can penetrate the material much more easily, so that you can use it to start detecting things that are deeper inside the fruit than just on the surface or in near surface layers. It is a quite established method, of course, for many purposes, mainly in medical applications, but also in material science. It is used quite a lot. Quite some research infrastructures that supply the technology. And we see it also more and more used in the food industry, where it is being used on quality inspections lines for detecting foreign objects in packages to avoid that unwanted materials go into the supply chain. So we're trying to establish how we can use that method to use for non-destructive evaluation of the internal quality of fruits. So how does it work? X-ray imaging, and here you see a kind of a schematic setup. So you have an X-ray source that is producing the X-rays. They are emitted onto the material here in the middle, which could be, for instance, a fruit. Some of these X-rays would be absorbed by the fruit depending on its internal density distribution. And you can imagine that if you have a defect, like for instance the cavity, then you have locally no density anymore, so you will be able to pick that up in the image, and the image you kind of assemble on a detector, which is on the other side of the material. So it's really a nice method to visualize structures, and here's an example of how you would use it, and you can create these type of 2D pictures from it. It's quite a fast method. Within milliseconds, you generate these pictures, so this is potentially very suitable for inline sorting, where we are also moving at speeds of several fruits per minute. Of course, this is a 2D picture, and it does provide us some detail of the internal of the inside of the fruit. It shows the main fleshy area here. It shows the core, which is empty, so it's not absorbing the X-rays as much, and that's why it's making contrast in the image. You see kind of a gradient, because, of course, here in the middle, the fruit is thicker, so it's absorbing more of the X-rays, and here on the edge, there's less absorption. But overall, this shows quite a uniform picture, and I would imagine that this would be then a sound fruit. A second method that we can use is what we call tomography. Is then we are actually generating a three-dimensional picture of the object or the fruit. And in this case, we would move either the source and the detector around the object, or we are rotating the object itself while it's passing through the X-ray system. And then we use some kind of complex mathematical operations to re-establish the three-dimensional picture of the fruit, and that would look something like this. And then you can see that you get the details of the internal structure much better, and you start to see also all kinds of gradients within the fruit structure, which give you an idea about the internal structure, and that's what we are after. So to use it for internal quality inspection, this is kind of an example of, again, a Braeburn fruit, the same fruit that had been stored over several months, and every month we have taken it out of storage to do a scan, and you see how it is developing the internal disorder. Actually, here's the sound fruit. We see the core of the fruit with the pits. We see the vasculature structure here, and with the experience that we have, we can probably say that this is at harvest. This is a healthy fruit, and then you see things are changing in the internal structure as storage is moving on. And then when we would have cut open the fruit here at the end, we would see that it indeed had severe browning, and there's also cavity formation here. But our non-destructive method is picking up those things quite nicely in every stage of the development. Of course, for post-harvest applications, we can do this on these fancy scanners that we have in the lab. But of course, the industrial setting is something quite differently. We need things that can be used for inline inspection. One option is that we would use this 3D CT scanner, and then instead of putting here a patient on this bed, we can put in a conveyor belt where we can transport our fruit on and do the scans. This is one of the options that could be looked at, and there's one supplier that is trying to put even a system like that in the market, but you can imagine this is quite an expensive setup. Hospital scanner easily costs, I'm thinking in euros, could be €1 million for one device, so this is probably outside of the cost benefit range of an industry like ours. So we should be looking at more cheaper options, and this would be systems like on the right-hand side, where we just have a 2D scanner producing these 2D pictures. Again, with a conveyor belt, a simple setup with a simple sorts and a detector, and this will be a much more cost-effective solution for what we use it for, and would be compatible with the speeds that we would need on sorting lines. So we'll be looking at this type of methods and use the left-hand ones as a kind of a reference for our research. So here's an example where we have scanned pear fruit after codling moth damage development by the larvae that had been deliberately kind of used in infestation studies to deliberately create damaged fruit. And here's an example of a 3D image, a slice of a 3D image on the left-hand side where you see where the larvae is and its cavity that it has created in the fruit. And on the right-hand side, the corresponding 2D inline X-ray pictures on the machine that I just showed you. So the left-hand side picture took us probably 5 minutes to generate this picture for a single fruit. So that is really not what we need in practice. But the right-hand side picture took us fractions of a second to generate. And it also outlines where the damage is in the fruit if you look well, although it is a more shallow picture than the one on the left-hand side. Here you see that the 3D imaging would allow us to easily detect all these defects. Here's examples of larvae infections at different development stages. You see in each of those images, you will see the red area popping up where the infection has been taking place. So it's very easy to find those in these 3D images. And to use these images for classifications would not be that big of a challenge. But of course, again, we are working with this 2D X-ray data. And here's another example of apples that have developed browning inside. Left-hand side is the healthy apple and a scan of that. And on the right-hand side, you see a defect apple and it's scanned. And this is more challenging to see which one is now the healthy one and which is the more defect one. And that's where our artificial intelligence is coming into the picture. So we need to deal with these pictures and make a reliable decision on which one to sort out and which one to keep in the rest of the chain. So we need to do what we call classification based on those images. We need to find computer algorithms that can, based on the pictures that we feed into the algorithm, then make a decision for us whether this is a healthy or a damaged fruit. So on the left-hand side here is a 2D X-ray image of, again, an infested fruit. You see the damage created by the larvae infestation. And in the end, we want to make a decision on whether this fruit is ready to go or we should move it out of the supply chain. One way to do that is by a conventional method of artificial intelligence. Artificial intelligence is kind of a broad term that covers kind of all kind of computer algorithms that make decisions for us that we would make by we can inspect this picture ourselves and make a decision. Yes, this is an infested fruit, but we should learn actually the computer to make that decision without our intervention. And one of the methods in artificial intelligence is machine learning. That's been around for quite a long time. And what that means is that you kind of do all kinds of computations on this image to get to a stage where we have what we call features, which are all kinds of properties of these pictures. It could be, for instance, that we want to find the volume of this part of the image here that we would define as the damage area. It could be things related to the intensity of the image. So we can have tens or 100 or more than 100, several hundreds of features that we can imagine that we can calculate on this image that might be relevant to make a decision on. Then the challenge with machine learning is that you have to make a selection of which of those features are really relevant. And then you can feed them into what we call a classifier, and then the classifier would make a decision for the end result. Here's an example of how we do that for pear infestation, the insect infestation case. So here you see again 2 X-ray images of, on the left-hand side, a healthy pear, on the right-hand side, an infested pear. We can start processing those images with what we call thresholding, and we can do local thresholding, and that will outline the contour of the fruit as well as changes in kind of density inside this fruit here. So it highlights kind of the cavity, the core cavity of the fruit here, but also other spots where we see density changes. And this allows us to also kind of identify the areas where the infestation has taken place. We can kind of clean up that picture a bit more to avoid noise in the picture, and then the healthy fruit just shows the core of the fruit, while the defect pair shows the core of the fruit as well as the areas where the damage has occurred. Combining that with a global threshold, so to just see the shape of the fruit, we can actually find where the potential problems might be in the picture. And it's the properties of these areas then we use in the classifier to say the left-hand side should be attributed to a healthy pair, the right-hand side where we have more dots distributed across the pictures, there probably this relates to a bad pair. And we can calculate, feed that into what we call classifiers. I'm not talking about their particular algorithms and so on. But depending on the parameters that we use here, we can have higher or lower success in our classification. And here it is ranging somewhere between 56% of success of the classification. And we use, of course, our benchmark here, which are the cut open images, so we know which ones are bad afterwards. Up to 68%, which of course is not great. And depending on the parameters that we use here, we can have a higher success rate or lower success rate. But you immediately see, while using this conventional machine learning methods for this kind of problems, we're running into limitations. Classification success of lower than 70%, I assume that you would not be happy with that and you would not accept that as an industry. Instead, another method you can use that is getting more and more traction today is deep learning. And probably all of you have heard somewhere a little bit already about deep learning. All these artificial intelligence programs that you use nowadays to help you write texts, ChatGPT-like things are also deep learning methods. So these are the new kind of AI-type algorithms that are replacing the machine learning ones. And instead of what we had just done, that we ourselves need to think about how are we going to process these images and which features do we have to calculate, you just let the algorithm do it themselves. You just feed these images into the AI algorithm, the deep learning algorithm, and it's going to do all kinds of operations on those images. It's going to do millions of operations instead of what we did with where we have 3 or 4 operations with a few parameters. This algorithm will do millions of operations, so it can do many more operations that we can even imagine. And that is the strength, of course, of these methods. And in the end, it will also generate a kind of a feature system, and it will then again doing some kind of classification on them to make the same decision. Here's an overview of these kind of deep learning convolutional neural networks that are typically used for this image processing. You see on the x-axis here the number of parameters that they use. Indeed, it is millions. It goes from 20 million number of parameters up to 180 million of parameters. And on the y-axis, you see the accuracy of classification on a set of images that are available on the internet. It's a huge database of images, and it has been tested to classify images of cats and dogs and cars and traffic lights and whatever. All these kind of images that you have supplied also data for when you have to log into web pages where they have asked you to mark certain items on pictures, and it's actually these pictures that are used now to train those algorithms. And here you see how the accuracy goes up as these deep learning methods have been developed over the years. And typically, you need more and more parameters to create, to increase your accuracies. And then at a certain moment, the researchers say, but now it's becoming a bit too complex, these networks. So they start again with novel concepts, and they will get more efficient networks that are performing even better. And from our perspective, in our sector, we're not into development of these networks. We are very lucky. All those networks are freely available. It's very open society, so we can just use them and see how they can work on our applications. So I'm going to skip a few slides because of time. And here's how we apply it to our infestation application. Codling mod infestation. The problem, of course, now is we have these huge networks with a lot of parameters. You can imagine you have to optimize those parameters, so you need also a huge amount of data now suddenly. And of course, in our sector, it's not easy. Certainly, if you want to study things like this, you don't know whether you're going to get codling mod infections, so you can either do dedicated infestations like we have done in laboratory conditions, and we can get a number of infested fruit in the 100 types. Or we can do these infestations in the field and then get even lower numbers of infested fruit. So it's the main challenge of using AI in our industry is, do we really have enough data for the AI to work properly for us? In that sense, we need to also think about training strategies. So we have these pre-trained networks with a huge amount of parameters. Do we need to train all those parameters? Probably not. We can maybe just fine-tune a number of those parameters for our application because it has already been validated on image classification. And here you see a result of how we can use the AI for classification on the infestation case. You see we can reach accuracy up to 95, 96%, which is much better than the below 70% that we were able to do in the past. So it's really showing us benefits. Depending on how many parameters we can actually optimize and so on, it will be better and better. And depending on which kind of network we take, it will be better than another one. So that, of course, there's work to do on finding these optimal conditions, but we see we can get accuracies that are much better than in the past. And here's also an interesting example where we compare the AI algorithm, which are the marked bars here on this graph, with the conventional, the marked bar is the benchmark method, so the machine learning method, and the ones without the marked bar are the deep learning methods. And here we have different data sets of infestations, and we see that each time the deep learning method is outperforming our reference, which is also given here in these numbers where we're looking at the accuracy, the precision, and the recall of the classification. And every time we see that the deep learning method is really outperforming the conventional method across all the data sets and across all the types of infections and stage of infections. So we're very happy with that. Of course, there's still an issue about explainability of AI. We were looking at this large network. We just let the network do and make its decision, but we don't know why it is doing that. And so we should be careful about explainability of it. With the conventional machine learning, it's easy because we know what we are doing. For instance, we are looking at these spots in these figures, but we don't know whether the AI algorithm is actually doing that. It might be that the AI algorithm is looking at the corner in this image here, in the upper corner, because something is happening in the image there that is not related to the infestation at all. So we should be very careful because we're just generating numbers and we don't know what they actually mean. So we need methods to help us identify where the AI algorithm is looking at, and we can do that by using what we call class activation maps. They highlight the part of the figure where the algorithm is looking at. And here you see again for the infestation case, which part of the image are being used actually by the algorithm, and we are confident here that it is looking at the right areas. It's always the areas where the actual infestation is taking place. So we're quite happy with this result. I'm going to skip this. There are other methods that we can use in AI than the one that I've introduced, where you don't even have to train and use large data sets. There's quite interesting progress there. There are other type of approaches that introduce even more explainability, like vision transformers, which act much like these language models that are used by ChatGPT, but then for vision technologies. Deep learning is not always the best way to go. That's also a message that I want to convey. And sometimes the machine learning method, which is on the left-hand side here, using multi-sensors where X-ray is combined with other methods, outperforms the AI-based method still. So we should also be careful not to rely on AI for everything and every detail. So as a conclusion, the key messages that I want to convey from my introductory speech here is that we're now introducing new imaging technologies that are feasible for internal quality sorting in a reliable and robust way based on X-rays. That image processing is crucial in this kind of approaches for correct classification and use. We have to be aware of the accuracy of the methods and how they can be generalized, which means that we have to, once we have the algorithm, that it also works on a new data set. If we use AI, the amount of training data is of concern, but there are methods, as I said, that don't need that large training data also. And we need to do a proper validation and testing of the methods before we can deploy them in the field. And the final message is, okay, there's a tendency in the AI community to keep on making larger and more complex networks just because they have the computational resources, but that doesn't always mean that it is more efficient or better than doing it the old-fashioned way. So also there, we still need the experts in the field to help us choose the right methods. But we're happy to progress that area and do this with you. Thank you.